Today's focus will be on graphing. As you guys know, a graph is a visual diagram that illustrates the relationship between two or more variables being studied. So we could have bar graphs, you could have line graphs, you could have pie charts, something like this, let's say. Okay, you could have pie charts. In this class, we primarily will be doing line graphs. Line graphs do a really good job of explaining overall relationships between two variables. All right, there are a few components that every graph will need, okay, especially every line graph. First, you need a title. You will write the title at the top of the graph, and it will always be written in the format of dependent variable versus independent variable. Now, the dependent variable is not literally written as dependent variable versus independent variable, which I have gotten from students. You want to apply it directly for your graph, so mass versus volume or something like that. I'm going to skip the dependent variable because I actually think the independent variable is the easier to identify. And the independent variable will always go on the x-axis and always include your units. Okay, so if you're putting volume down, how did you measure volume? Did you measure volume in milliliters, in liters? What did you do? Okay, and that will always go on the x-axis. So the independent variable always goes on the x-axis. How do you identify what it is? The independent variable is the variable that is being controlled, which means it is what I changed. Okay, so the independent variable is what I changed in the lab. So it's I. What did you directly change? So I always remember what I changed is the independent variable. So think through the lab. What did you directly change? That's your independent variable. It goes on the x-axis. Now, because you changed the independent variable, your dependent variable may change, okay? And that's the variable that responds to the change. So that goes on the y-axis, and you write down the units, okay? How I remember that it goes on the y-axis is you have your graph, and you can put a D on it. So this is your dependent variable, is on the y-axis. Okay, another saying that I always hear is, why are you so dependent on me? So the y always has the dependent variable. Okay. The slope is the thing that for every change in y is for every change in x. So its symbol in an equation is m, and you always follow it the rise over the run, or the change in y over the change in x. So what you do is you need to find two data points. So let's say y2, and then you subtract it from y1. Remember, this is your y's. And then you're going to divide it by your x2 minus x1. Now, the key when you're calculating slope is, number one, you need to make sure that even though you write in the x, y coordinate system, you actually reverse and put the y on top for when you're applying it to slope. And then the other thing is that you need to make sure that you take your second set of data points and subtract it from the first. And then you do the same thing. You take your second set of x values and subtract it from the first. It actually really doesn't matter if you take the first and subtract it from your second, as long as you do it both for the y and the x. You have to be very consistent with it. All right, so let's just try to apply this parts of the chart to, or parts of a graph to this graph, okay? So a ball is dropped from several distances above the floor in meters, and the height it bounces is then measured in centimeters. Create a title and write the variables on the appropriate axes. So what I always like to think about is, what did I directly change? Because whatever I directly change will go on the bottom. So I changed in this thing the distances, I dropped it in meters. So I'm going to write distance dropped, and then you put the unit parentheses meters. Okay, and then what changed because I changed the distance it was dropped from? I'd write height bounced. And then once again, you need your unit, which would be centimeters. Okay. Now you need to create the title. Now we read, one way you can remember this is you always read left to right. So what do we run into first? We run into this guy first on the y-axis, and then you run into your x-axis. So you're going to write height bounced versus distance dropped. Okay, and so that's where you get your dependent variable versus your independent variable. You won't be writing the dv and iv, obviously, but just to explain. All right, the equation of a line. So a lot of the times in this class, you will be generating an equation of a line, and the equation of a straight line follows this format of y equals mx plus b. okay? And you guys should be very familiar with this. Y is the value of Y at that data point. X is the value of the X at that data point. M, we've already talked about, is the slope, so the relationship between the change of Y over the change in X. And B is your Y-intercept, okay? The Y-intercept is where the line actually crosses the Y-axis. So most of the time in this class, it will be 0, but not always, so don't always assume that. Okay, so here's an example of it. So we've got a rise to calculate slope. So we have two data points. We have a 4, 3 and a 1, 2. Remember, this is your X and this is your Y values. Okay, so you always go X then Y. And so what you need to do is you need to calculate it. So we're going to take our change in Y's, okay, which is 4 minus 1, which is fine. Oh, that's your X's, sorry. You're going to take 3 minus 2. So I'm going to take 3 minus 2. And then if I take 3 minus 2, then what I need to make sure is I take 4 minus 1. And all of that's fine as long as you're very consistent in the direction. Notice my arrows over here are always going from one to the other. It doesn't all of a sudden go back that way for the Y values or the X values. You have to keep going in the same direction. So when you do that, you get 1 over 3. And does it look like a 1 over 3? Don't count the blocks because that doesn't work in this class. What you want to do is, does it look like it's a positive slope? Yeah, it's going up. Okay, so it would have a 1 over 3. That makes sense. All right, you also are going to be expected to make graphs according to the scale. And so these are the different steps that you want to do. First off, increments must be equal within an axis. So within all of the y-axes, the values of each box have to be the same. But both axes don't have to have the same increments. So just because I go up in tens, each box on the y-axis, does not mean I need to go over 10 in the x-axis. Okay, not all graphs have a y-intercept of 0. Okay, and what you want to do is you want to take up as much space as possible. So these are the different steps that you're going to want to do. Okay, and we'll do this on the next one. Okay, so in order to set it up and make sure that you are using as much space as possible, follow these directions. So first, find the difference between the high and low data point for an axis. So we're going to take the difference of these guys. So we're going to take 90 minus 70. Okay. So the example is take the difference, we got that. Okay, if you want a y-intercept of 0, 0, then da-da-da. Okay, we don't care yet. All right, because we're not going to make these equal to 0. So we didn't take measurements at 0 degrees Fahrenheit. So we're not going to bother putting it there. Okay, and we also don't know when millions of ice cream cones would be sold, so we're not going to deal with that. We're just going to take these values and not force it at 0, 0. Okay, so we're going to divide the difference by the number of boxes along the axis. So I am changing directly my temperature, and because I changed my temperature, the ice cream sold changed. So this is going to be my x-axis, this is going to be my y. So on this, I've already counted, there are 10 boxes. So what I'm going to do is take my range, which is 20, and I'm going to take 20, and I'm going to divide it by however many boxes I have, which is 10. And so each box is going to be a value of 2. Okay, so this one right here is going to be 70. And then I'm going to just do every 5 because I don't have a lot of space. So this would be 72, 74, 76, 78, 80, 82, 84, 86, 88, 90. So did I go from 70 to 90? Yes, I did. I need to now make sure I label it, and I'm going to put my temperature down here, and I'm going to put degrees Fahrenheit. Okay, and I used up the whole box range. That's awesome. Now let's try to do the exact same thing for the top one. So we're going to take 6.0 minus 5.0. So that is a range of 1. Okay, and then we're going to divide by however many boxes I have, which is 10. So each one is a decimal of 0.1. Okay, now it is key to note that if sometimes you don't get a whole number like 2.25, it's a lot easier. First off, you will always have to round up. You never round down because otherwise you'll run out of boxes. But it'd be a lot easier to count. Instead of 2.25, you make every box 2.5 or 3, depending on what is the best situation for you. Now, knowing that, you will not use all of the graph, but you will use most of the graphing space. Okay, so now I'm going to do the side ones. I'm going to start at 5.0, and I'm going to do every 0.5. So it's 0.1, 0.2, 0.3, 0.4, 0.5. So this is 5.5, 0.1 or 0.6, 0.7, 0.8, 0.9, and then this would be 6.0. And now I'm going to label it. So this is ice cream sold, and then I'm going to say in millions. of cones. Okay, and there you go. All right, so drawing a line with a specific slope. This is a little bit trickier, but you will be expected to draw a line of a graph that has a specific slope. So here's the steps how you do that. Here's the example problem over here. So graph a line with the following slope of 7 grams per milliliter. And what the first question you need to ask if you're trying to do a line is, what is the equation of the line? I know my formula is y equals mx plus b. Y is always a variable. In this case, I am telling you the slope is 7 grams per milliliter. My x is my variable, and in this case, I'm going to assume, because I don't tell you, I'm going to assume my y-intercept is 0, okay? If I don't tell you there is a y-intercept, then assume that it's going to be 0, which makes sense because if I have no mass of something, then I'm going to have no volume. So if I have no grams, I'm going to have no milliliters. So in this case, it does make sense that my slope would be, or my y-intercept would be 0. If you want to write it, you can put a 0 if you want. Okay, so plug this in the equation and solve for y. Okay, so, use the equation. We did that. Choose any value of x. I'm going to do this 3 times. I think 3 data points is better than just 2. So even though you can do it with just 2, you absolutely need 2. You don't need 3, but we're going to do it for 3. My first data point I'm going to choose, I'm going to make it equal to 0. Okay, so I'm going to plug in 0 into this formula. My formula really without units is y equals 7x. So my first one is, if I put in 0 for this guy, for x, you choose your first one. Okay, you choose your x value, and from there you solve it to figure out what y would be. If I do 7 times 0, I would get 0. So my first data point would be 0, 0. I'm going to try another one. And you kind of want to move along. So I look at these axes. I'm like, okay, there's like a 10 down here. There's a 6 down here. I want to use as much of this graph as possible, so I'm going to try to expand on it. So my next data point I'm going to plug in for y equals 7x. Okay, remember this is the slope that I gave you. I'm assuming my y-intercept is 0. I'm going to choose another x value. Always choose x because it's easiest. I'm going to choose 4. So I'm going to take 7 times, actually, I'm not going to choose 4. I'm going to choose 1. Okay, so I'm going to choose 1. And so if I do that, I get 7 times 1, which is 7. So I'm going to go over 1 and up 7. Okay, here's my problem with this graph, actually, as I'm running across this problem. I'm going to choose another number. So y equals 7x. And this time I'm going to choose, let's say, 10. Okay, so I'm going to say my first x value is 10. So when I plug that in, I get 7 times 10, which is 70. So I'm ready to go plot it, because this is what actually happens. It is 10, and now I go over the 10, and now I have to go up 70, and I ran out of a lot of space. So I know that value, even though it's correctly calculated, I can't plot it, so it doesn't help me actually draw the line. So you do have to sometimes guess and check, and sometimes you'll overcompensate, but make sure you try to use as much of the graph, because what I find students doing is sometimes they'll like crunch all their 3 data points like right here, pretend that these were them, and then their slope looks totally different than if they had expanded out a little bit, just because of how crunched they were trying to get it. So if you can, try to choose an x value that's further on in the thing, but obviously for this case you can't. And then you have to connect the dots. Okay, so here I'm going to connect the dots using a straight edge, aka a ruler. Harder on a computer screen, and there you go. That is something with a slope of 7 grams per milliliter. All right, the last thing well, one of the last things is drawing a best fit line. So because we take a lot of data points, our measurements are a little bit flawed. And so because of that, you want to take as many data points as possible. And so when you get the average of all these values, you get your best case scenario relationship. The exact same thing happens with a graph. When you take a line and you do a best fit line, okay, what you're doing is you're taking the average of all the data points to figure out your best relationship average. Okay, so after all the data points, what is your best average? So how do you do that? First off, in this class, that's primarily how we almost never connect the dots. Okay, a straight line drawn through the center of a group of points. Okay, that's the best fit line. It's a line. You never connect the dots. You always need to use a ruler or a straight edge, just anything that's straight. And the purpose is to determine the trend or relationship between the variables. Find that average. Okay, so after plotting, these are the steps that you want to use. So after plotting the points, visualize the trend and where the line should go. Draw the line with an equal number of points on either side with, just try to get the best average. The distance of the points above should roughly be the same as amount below. All right, so let's try to look at some of these examples. So I've gotten kids who are like, oh, here it is. That's it. Well, is it the best line? I agree that that's an average because I have 3 dots here and 3 dots here. But isn't there a better relationship that you could draw? And so what I would say is that I would get out my straight edge and I'd want the same above as below. And so I draw a line like this. Okay, and now that's not even the best because it should go down a tiny bit more, I would say, but I wouldn't take off points for that. Okay, so obviously now I'm really close to all of these data points. I don't have any ones that are extremely high or extremely low, and that looks like a best fit line to me. Now trying the next one on the right, I would go more like this. Okay, that would have a negative slope. The one on the bottom left, okay, and then in the middle, it looks like it's slightly, if I just squint my eyes, the general line, it kind of goes very slightly upwards. It's not a completely horizontal line. So these would be examples of how you do the best fit line. Now the problem with the best fit line is if somebody drew this, well, that's completely wrong. But let's say somebody drew it more like this. They just eyeballed it and they got a line, oh, just a little bit lower. And somebody else drew it and they're like, no, that's not the best case scenario. It's more like that, okay? Now, one of those is probably better than the others, but in reality, is it exact? Like, is there a huge difference? No. And so all of these are correct. The best way to do it is actually to not have to draw your own best fit line. It's better to use a graphing computer like with an Excel, and they'll do it for you where it mathematically calculates where the best average actually is between all those data points. So, all right, so there are 3 types of relationships you will absolutely need to have memorized for this class. We have direct, indirect, and inverse, okay? A direct relationship is that X increases, Y increases proportionately. Basically, what you have is a positive slope line. Okay, an indirect relationship is as X increases, your Y decreases proportionally. So what that's basically saying is that you have a negative sloped line. Still a line graph. Okay, and then an inverse relationship is as X increases, Y decreases disproportionately. What you have for that is kind of like what I call the ski slope. And you'll see examples of this in a second. All right, so here's the relationships of the graphs. Here's your negative sloped line, so that would be your indirect relationship. So as X increased, Y decreased. Direct relationship, I have my line, as X increased, Y increased. And then in my inverse, as X increased, Y decreased disproportionately. So it looks like that ski slope. So we have a negative line slope is indirect, positive slope is direct, and a ski slope kind of downward is an inverse relationship. All right, hopefully you have a basic review of these graphing techniques and have fun with the practice.